We looked at a linear function in the last video, and we saw that there is a fast way to do it, where I don't have to use differentiation from first principles. So that's linear. Why don't we have a look at quadratic? Now, you can pause the video and you can do your differentiation from first principles if you'd like some practice. I'm just going to do it quickly because there is faster ways of doing it. So if you went off and did it by first principles, you'd have a load of work, and eventually you'd find out that the differentiation of this is 6x plus 2. I'll explain how I did that fast in a few minutes, but I guess what we noticed before was when it was linear, we could use our coordinate geometry. And we could do it a fast way that way. You know, it's the slope. But if you think about a quadratic, you know, I'm just going to sketch any quadratic, not that particular one. If it looks like this, then do I really have over 1 up 3, over 1 up 3, a consistent slope? Or does the slope change depending on where you are on the function? Like here is a slope of 0. Here is a slope of, let's just say, approximately plus 1. Well, then here approximately is approximately minus 1 of a slope. So it makes sense that if I differentiate a quadratic, that I don't get a constant number like I did for linear. A linear is just a straight line, whether it's a plus slope or a minus slope, over 1 up 3, over 1 up 3, etc. Whereas a quadratic, it just depends on where you are on the function as to what the slope is. So no wonder I got a variable in my answer. So if I have the function 3x plus 2 and I differentiate it, I'll get the slope of 3. But if I differentiate a quadratic, I'll end up with the formula for the slope of the line. I won't end up with a constant because there is no consistent answer for a quadratic, for the slope of a quadratic. It depends on where you are on the quadratic. So formula for the slope of the quadratic. That's the basic idea. Again, if it was a cubic, you wouldn't get a consistent answer, you know. Depends where you are on the cubic as to what the slope is. So maybe here and here, you'll have a slope of 0. But here you'd have a slope of -1 maybe. Here you'd have a slope of +1. So when I differentiate a quadratic or a cubic, I'll end up with the formula for the slope of the cubic. You know, I won't end up like I did with a linear with just a number, a constant number. So it's just important to understand what we're doing. And if you can see here that, you know, we used information that we had from coordinate geometry to figure out a fast way of finding the rate of change of the function. Well, there must be other fast ways. I don't have to do it by differentiation from first principles all the time. Often, you know, a mathematician will see a pattern and they will like do it fast if they possibly can. So this is where knowing how to use your log tables is really important. Okay, you want to be able to understand what this whole page means. I'm going to start on the left bit here, and then there'll be other videos for these. And what do I notice? They tell me if I'm given a function and it looks like this, or this, or this, or this, or this, or this, you know, then this is the rule that you apply if you want the differentiation of that function. Now, the only thing is, I have to understand that the x is, you know, it's going to be a variable. N is going to be a number, you know, so x to the power 3, x to the power 2, x to the power 1, x to the power 0. It doesn't matter what the power is, but you have to have, you know, your variable, and up here has to be a number. And that's how I did the previous one fast. So when it looks exactly like this, I apply this rule, and that'll give me the differentiation of it. So I'm just going to show you now slower how I got this. So if the function is 3x squared plus 2x plus 9, I'm always going to want to use this if possible. You know, this is the first place I check, and I can see that the very first thing I want to differentiate is a 3x squared. Okay, so a 3x squared, so there just happens to be a 3 in front of my x squared. You can bring the power down in front. So the 2 is going to come down in front to be multiplied. And I'm going to subtract 1 from the original power. 2 minus 1 is 1. So that differentiates to this. I'm going to clean it up in a second. The next little bit, I'm just going to put a line here just to show you I'm on to this one here now. So what's the power here? I have a 2x. So even though it doesn't say it, it's an x to the power of 1. What does it say? If I have, you know, an x with a number, then you can bring the number down in front and subtract 1 from the original power. So the number goes down in front, and I subtract 1 from the original power. So that's that part done, and I'll do that in a minute. Clean it up. And then here, I don't have an x to deal with. Well, technically I actually do. I'm going to put in an x. So anything to the power of 0 is 1. So I haven't changed this, I've just rewritten it to suit myself, so I can use this rule here again. So I've changed nothing, just rewritten it so that I can bring the power down in front and subtract 1 from the original power. Okay, so all that's left for me to do now is clean this up. 2 times 3x to the power of 1. Sorry, that 1 should be there. It's just this I subtract a power from, not, you know, the 3x. It's just the power of the x that I subtract 1 from. So that gives me 6x to the power 1 plus 1 times 2 times x to the power 0. Well, anything to the power 0 is 1. 1 times 2 times 1 is what's there. Plus 0 times anything is 0. So I end up with 6x plus 2 plus 0, which gives me 6x plus 2. By not doing differentiation from first principles, and just by knowing how to use my log tables correctly, then I can, I mean, I'll get much faster at this as well. This is just my first time going through it. I can use the rule, bring the power down front, subtract 1 from the original power to get my formula for the slope at which, or the rate at which, yeah, the same thing, the slope or the rate at which the function is changing.